So there's a lot of different ways of thinking about the scientific method, and the scientific method is not really one thing, and different textbooks will describe it differently. But this is one way of thinking about it, that you kind of have scientific understanding on top, and then it's built on these three foundations. So one of those foundations is observations. You observe something out in reality. And so that's kind of your starting point, is that you want to explain something about the world. So in the case of climate change, we observe that the world is getting warmer. And so observations don't necessarily mean that you've seen the thing, right? Because we know that things can be detected that we can't actually sense. So it could be that you sense it through through one of your other senses, so one of your other five senses, or it could be something that's imperceptible to humans, right? So we talked a lot about long wave radiation, which is not perceptible to us. So if you have some type of a device that can measure something that's not something that we can actually sense with one of our five senses, that can be an observation as well. So first you observe something. So observations are a critical part of scientific understanding. And then experimentation is a critical component. So experimentation is, you're thinking about that you've seen something, you've observed something, you've detected some phenomena. And explanations, you want to explain it. Explanations for the observed phenomena are tested, and you're testing them by kind of intentionally manipulating conditions in experiments, using well-defined experiments. So this is often expressed in the language of hypothesis testing. So experimentation tests hypotheses of explanations of observations. So you observe something, you have some underlying hypothesis for why that thing is observed. And then you can kind of design an experiment to test whether or not that your hypothesis is true. And so usually that's expressed in like an if-then type of statement. So if my hypothesis is true, then we expect the experiment to turn out this way. Let's say I observed that if I mix chemical A and B and it produces an explosion, but then I also observed that I mixed chemical A and B and chemical C was present and there was no explosion produced. Then I can design an experiment where I do it again with chemical A and B, and I can see what happens, and I can do it with chemical A, B, and C and see what happens, and repeat that type of experiment over and over again and see whether or not my hypothesis that say like chemical C neutralizes the reaction, if that is true or not. This is, it's very basic common sense stuff that we're doing all the time. Like we're constantly testing hypotheses, and even, I've noticed animals are constantly testing hypotheses. So this is a picture of my dog, Mika, and I've noticed that she does this hypothesis testing a lot. So what she'll do, she really likes to play fetch, and with toys or balls that she has in this like bucket in the corner of the living room. And so she'll often bring me a ball like this and do the sad puppy face, and she wants me to throw it, and she like never gets tired of that, and she'll have me throw it forever. And often I'm busy and I don't want to do that because I have other things to do than just throw the ball for her all day, which is what she would want me to do. And so we do this command, we say like not playing. And I noticed that she'll do this hypothesis testing. So she observes that I am not engaging with her, and she has a hypothesis that it's not that I don't want to play fetch with her, it's that I don't want to play fetch with that ball. And so she'll go and she'll get another ball. She'll like wait there for like a minute, and then she'll go and get another ball from the corner and bring that to me and test that hypothesis. And so then I still won't play with her, and she'll be like, okay, maybe it's not, she doesn't want to play with that ball either. And so then she'll test like 2 more balls. And it's amazing that she's doing this hypothesis testing. And so eventually, if I don't give in, then she'll unfortunately have to come to the conclusion that, okay, it's not actually any particular ball he doesn't want to play with, it's that he doesn't want to play overall. And so that's very, very sad. And then she'll go and mope in the corner. But another thing that I noticed with my dogs, and I think the lesson here is about designing your experiment very precisely, is that they, everyone knows dogs bark at the male person when they come by. And so our dogs are no exception. They bark every day at the male person. Their hypothesis is that when the male person comes, they're an intruder, right? And they are barking, and the barking is scaring the male person away. And so their kind of experiment is, okay, every time the male person comes, I bark and the male person goes away. And so they're kind of confirming that over and over again, like in their head. And so they have to be a little bit more careful with how they're designing that experiment if they really wanted to get at the truth, right? They would have to say, okay, tomorrow, the male person's gonna come and we're not gonna bark. we're going to see what happens. And if they still go away, then maybe it's not actually causal, that like our barking is causing the male person to go away. So that's just, it's a lesson that you can be kind of fooled with how you're designing your experiment, that you can think that you've proven something to be true when you haven't necessarily. So in addition to observations and experimentation, that often leads to models. So if you have enough observations and experiments, you can create a model. And in climate science, we use models a lot, often called global climate models. But a model is just a general thing that we use kind of in all sciences. And it's just a simplified conception of the phenomena you're interested in. It has to be simplified, because if it wasn't simplified, it would just be the real thing. So it's simplified in the sense that it retains the essential features of how you think that thing works. So modeling is kind of our third pillar here. And then on top of all of these things, underlying our scientific understanding would be like our theory of how the thing works. So theory is kind of just our conceptual framework or underlying explanation that makes sense of all of our observations that we have and makes sense of the experiments that we've run, and is also consistent with the models that we've put together. And so theory is like this confusing word, because scientific theory is not, the way that we use it colloquially. That's like an untested speculation, where you say like, I have a theory about this, and that essentially means that like I just came up with this guess of how this works. And so it's not that. Scientific theory is not that. It's basically the highest level of scientific explanation that an explanation can rise to is to be a theory. But it's also not like, just a stamped fact. So you can't just say like, well, it's a theory, so then it's true. So there's competing theories. A lot of times you have observations and experiments that are consistent with multiple theories, and so you have competing theories. And theories evolve over time. Sometimes theories are completely discarded, that it seemed like observations supported the theory, but then new observations come along that don't support the theory, and so you have to discard the theory. I see this kind of discussed with the theory of evolution. Often comes up. The dialogue is kind of like, evolution is just a theory, but did you know that actually gravity is also just a theory? And so then the implication is kind of like, well, if gravity is a theory, then all theories are like as true as gravity. But that's a little misleading, because there is gravitational theory. There's a theory of how gravity works the way it does. But the fact that if I drop my phone and it falls to the ground, that's not the theory of gravity. That's an observation. So if I drop my phone and it goes to the ground, I can observe that, and I can do a bunch of experiments that show how objects move around. But that's not like the theory of gravity. The theory of gravity is like kind of the underlying explanation. And Newton had a theory of gravity, and it turned out that that works in most circumstances, but doesn't work for very large objects in the universe. And so then Einstein came along, and he had a theory of gravity, general relativity, which works in more circumstances than Newton's, but doesn't work for very small things. So then we have quantum mechanics for that. So the theory is just the underlying explanation. It's not necessarily a fact, but it tries to make sense of all of our observations and experiments, and is consistent with our models. So this is our kind of framework that we'll use for thinking about a lot of different phenomena that we see in climate science. One more point just about kind of science in general is that I think that above all else, science is really about embracing an attitude about like being curious, about not being too wedded to your ideas, not being dogmatic. So yeah, curious about how the world works, open-minded to previously unconsidered explanations. And then, when you're designing experiments, you want to be careful and methodical and quantitative when possible, and avoid confirmation bias. So confirmation bias is that, you have a preconceived conclusion, and you try to assemble all the evidence that confirms your conclusion, rather than looking at, the full breadth of evidence, or even intentionally trying to prove your hypothesis or your explanation wrong. And if you try to prove it wrong and you can't, that's what makes the explanation really, really strong. And so one way of like thinking about this attitude would be that scientists, and I think we all should strive to be more like judges or juries, and not like lawyers, if we're going to use kind of the courtroom analogy. Or if you are going to be a lawyer, you should try the exercise of playing both sides. So you should try to be the prosecution, and then you should switch over and try to be the defense, and try to shoot down your own explanations for how the world works. It's ideal. It's an idealized notion of scientists that they do this, but unfortunately humans are really bad at this, right? We all get very attached to our preconceived ideas and to our conclusions, and scientists, form labs around things being true. That like, I study the impact of this chemical on people. And once that's kind of the way that my lab works, I'm going to have an incentive to kind of, you know, to look for that impact and to say, and the more impact I can find, like the better it is for my career and for my lab. And so scientists are not immune to this problem, but science in general, the idea is you have enough people kind of looking at things from different angles and with different motivations that what emerges from the scientific literature is basically as close to truth as we can get. Like, this is why you need peer review. If scientists were perfect, you wouldn't have to submit your article to peer review and have skeptical peers try to shoot down your arguments. You would just be like, well, I'm a scientist, I'm a perfect thinker, and I don't have confirmation bias, and so here's my report, and that's the truth. But that's not the way that humans are, even scientists that are kind of trained in this. So we think the best process is to have other scientists look at your work and try to find the holes in your logic. And then if it survives that and survives enough attacks after it's published, then we can think of something as being as close to the truth as we can get.